Okay, hello everyone. So, as I mentioned in the course introduction, today we are starting with some prerequisites, and in particular, we are starting talking a little bit about simplicial homotopy theory. Because if I understand, most of you don't know what a simplicial set is, and they're kind of a combinatorial tool that's very useful to model homotopy types. And the first half of this introduction will be a justification of the sentence I just made. And the second half will be using simplicial methods to actually define homotopy limits and co-limits and show how they work. So, okay. So we start with the following object. Start with the following category, delta, which is the category of finite non-empty totally ordered sets or finite non-empty posets. And the typical object here is of the form brackets n, which is this, which is slightly confusingly, but you'll see why in a moment it's called like that, the finite totally ordered non-empty set with n plus 1 elements. So, oh, and I didn't say it, but n monotone maps, of course. Increasing, no, non-decreasing maps, sorry. So, for example, there is 0, which is just a singleton, plus brackets 1, which is this guy. And well, I can put also brackets 2, this guy here. And there are maps between these objects, and actually let me mention a bunch of them. For example, there is the map that I'm going to call S from n to 0, which does what it has to do, since Si to 0 for every I. Okay. Hello, everyone. Can you hear me? Something funny
Yes, we
happened.
can.
Can you see my tablet?
Yes.
Okay, because I can't.
Yeah, but we can't see you. We hear you, but at least I don't see you. You are totally black.
Yeah, my computer has done something very weird. Okay, let's hope it's still working. Okay, everything seems to have. Let's see. Can you see me now?
No.
Okay, you will have to hear me. But if I move the tablet, you can see the tablet,
Yeah.
right? And you can hear me. Perfect.
Yeah.
Okay, sorry, I don't know what the issue is. Yeah. Okay, so we have this map. The constant map is going to call a degeneracy. And then there are going to be maps that I'm going to call di from n-1 to n for 0 less or equal than I less or equal than n. That's basically sending dij to j for j less than I and j plus 1 for j greater or equal than I. So it's identifying brackets n-1 with a simplicial subset obtained by removing the ith point. And just for completeness sake, you also have these guys here called the degeneracy maps. So these are called the phase maps. Makes sense in 1 second why I'm calling them this. but let me put all the definitions here. Sij is j for j lesser or equal than I, and j minus 1 for j greater or equal than I plus 1. And these, in order to make sense, we need 0 lesser or equal than I lesser or equal than n again. And this is essentially taking 2 points and collapsing them. So these things come from these names. These are also called degeneracy maps. These names come from a geometric perspective because we have a functor from delta to topological spaces. Oh, and let me mention it now for once and for all. When I say topological spaces, I mean compactly generated topological spaces. As in algebraic topology 2, we don't want to worry about crappy topological spaces. Let's consider only reasonable ones. Okay, we have a functor that sends n to what I'm going to call the topological n simplex, and I'll denote with bars delta n. And what is this? This is just the set of T0, Tn in Rn plus 1, such that Ti's are all non-negative and their sum is 1. And more generally, if you want, if you have an object here, you're going to set it to this guy. Oof. Yeah, let me call it S. So we do TS, S, and S in RS. But if every object is ordered from brackets n, so this is just a fancier way of saying things. And how is the functoriality working? Well, if I have a map f from n to m, I can send f of t0, tn to the sums t I wait. No, sorry. That's not correct. That's, well, let me call them t prime 0, t prime m, and that's just, sorry, t prime I is tj if, sorry, no, sorry. That was correct. What I was writing was perfectly correct. I just got confused because I wasn't thinking about some of these sums might be empty, in which case they're just a 0. Sorry, I was getting confused by that. It's correct. So concretely what it means. So, okay, well, this is just a point, the geometric 0 simplex. And this is just one simplex indeed. Right? You might have, if you take an algebraic topology 1, you might remember these guys from the definition of singular homology. You can take delta 2 and you see, well, I'm not very good at 3D drawings, but you have these guys here. And this is the point 1, 0, 0. This is the point 0, 0, 1. This is 0, 1, 0. So in fact, practically this is just the convex envelope of the basis vectors. And the face maps, the di from this guy to this one, are exactly the inclusion of the faces. Hence the name face maps. So this is all very geometric. Okay. And the degeneracy maps correspond to projections. You're collapsing two vertices together and you extend the map linearly. So for example, this S map from the topological and simplex here is just the, well, this is a point. So that's just the constant map at a point. Okay. Why am I doing all this? Well, 1 second. It's time to give the first important definition. So a simplicial set is a functor x from delta up, so it's contravariant to sets. Actually, I need to go to a new page. And I need to give you at least one important example. And you'll see why this definition now makes sense. So if X is a topological space, Sing X is the simplicial set that's in brackets N to hom in top, so the set of continuous maps from the topological and simplex to X. And that's actually the example that I want you to keep in mind for a simplicial set. It's not the most general, but okay. And the slogan is Sing X knows all about the homotopy type. Of X. And so given this example, inspired by this example, we'll often refer to X of brackets 0 as the set of points in X, and X brackets 1 as the set of paths in X. More generally, X brackets N is the set of N simplices. Hopefully, given this example in Sing X, the Sing X brackets 0 is literally the set of points of the topological space X, and Sing X brackets 1 is literally the set of paths. So, so this makes sense. And for example, you can probably see how from these you can define the singular homology of a simplicial set. If you remember the definition you've seen in algebraic topology 1, Sing X knows all that you need to define a singular homology. So for example, you can define the chain complex whose nth term is the free abelian group on X and face maps given by sum minus 1 I delta I. This shouldn't be a surprising notion. And so, for example, so X sees the homology, and then we'll see quickly how X sees also the homotopy, actually, or the higher homotopy. So Sing X really knows everything. But let me give you some more examples of simplicial sets before we move on. Or should I give the geometric realization first? No, let me give more examples first. So, another example is, suppose C is a category. Then we define its nerve as the simplicial set as n to the set of functors from n seen as a poset into C. So, for example, is the set of objects in C, and C1 is the set of arrows in C, etc. Oh, well, let me give you another one, sorry. Is the set of pairs of composable arrows. C, etc. And some of you took the algebraic K-theory class last semester. You might have seen this already and seen that this is in fact a fully faithful embedding of categories into simplicial sets. But we're not really going to use this. But the reason why I'm giving this example, besides it's going to be helpful in a couple of lectures, is that allows me to define delta n as a simplicial set, which is the nerve of brackets n seen as a poset. So concretely, this is telling you that delta n sends m to the set of monotone maps from brackets m to brackets n. And I want to think of this delta n as the analog of the topological n simplex that I discussed before. In fact, its zero simplices are exactly the vertices of the topological n simplex. Its one simplices are exactly the faces, the one-dimensional faces, what's the name, edges of the topological n simplices, and so on and so forth. And this guy comes with some important simplicial subsets. Okay, I haven't defined what a simplicial subset is, but essentially you give a subset for each x brackets n in a way that's closed under the maps. So for example, its boundary, you can think of it as union of delta n of every face for all I, and concretely this is sending m to the set of all maps that factors to a subset, so f is not surjective. So for example, you can think of the boundary of delta 0 is empty because every map to a one-point set is surjective. And the boundary of delta 1 is the union of 2 points. It's isomorphic to the union of 2 delta zeros. Because every map that's not surjective, either it's the constant map at 0 or the constant map at 1, and nothing else. Okay? Okay, that's one important example. And let me give another important example, and then I'll stop for questions. So for every I, you can take also the horn, which is the union of delta I delta n for every I different than j. All the faces, delta j. All the faces except the ith. And concretely, this means those f only instead of being surjective, the image of f does not contain the set 0 so the subset that's obtained by brackets n by removing the ith vertex. That would be like the image of the ith face, and we don't want that in the image of f. Copy it again. And so, for example, lambda 2, 1 is something I'm going to draw like this. It contains only the face opposed to the second vertex and the face opposed to the 0th vertex, but not the face opposed to the one vertex. And lambda 2, 0 instead is this guy. It contains the face opposed to the first vertex and the face opposed to the second vertex, but not the face opposed to the 0th vertex. And you can enjoy yourself and draw higher dimensional things if you're able to. Let me just try, I don't know, lambda 3, 1. So we have 1, 2, 3. So I contain, let me do actually lambda 3, 0, because that's easier to draw. So it contains this face, and this face, but not the face opposed to 0. And that's why it's called a horn somehow. Okay. Very good. Let me pause for 1 second and ask if you have questions.
I guess that I have a question. I guess that you can make the statements in the parentheses precise by writing them as appropriate colimits of those.
Yes, yes, okay. Yes. Indeed, I haven't explained, but in fact, it makes sense to take the union of two simplicial subsets by taking the smallest simplicial subset containing both of them. And then those statements are actually precise. And you are right that those are can actually be written as colimits. Okay. Other questions?
And is it true that the category delta is a model for the category of simplices in top?
It depends what you mean by a model. I mean, we are declaring it to be a model if you want. It's definitely not a fully faithful embedding.
That it is
because you're taking only linear maps.
Equivalence for the right category of simplicial, for the right category of simplices in top.
I mean, I would say yes, but it's kind of tautological again, because we are sort of declaring it to be and see that the theory works out fine, rather than having some deep reason to expect it.
Thank you.
Yeah. Okay, let me state now a proposition that usually is like the very first thing people tell you about simplicial sets, but I postpone it until relatively late for one reason, because I actually think it's less important than people usually make it to be, but we are going to need it. So we have a functor sing from top to simplicial sets, and this has a left adjoint, which is called geometric realization. Which has the form. Okay, concretely, this means that all homes of simplicial sets from X to sing Y are the same thing as continuous maps from the geometric realization of X of Y. And I can actually give you an explicit formula for this geometric realization. And this geometric realization of X is obtained by taking the disjoint union over all objects n in delta of a copy of the topological n simplex for every n simplex of X. And then I'm quotienting out by a certain equivalence relation, which says that for every f from n to m, every map in delta, and every x in x m, and every t in the topological n simplex, am I going to get this confused? F upper star of x comma t is x comma f of t. So for those of you that are categorically minded, this is secretly a coend, but I'm not going to mention the word coend ever again. I mean, there are some advantages of thinking very categorically, but I don't think this is one case of it. And so, for example, the geometric realization of delta n is, well, the geometric realization of delta n. You can actually see that this works in the way that it works. And then this preserves colimits because it's a left adjoint. So, for example, the geometric realization of the boundary of delta n is exactly the union of the faces of the proper faces in delta n. So for example, this is this guy, but without anything inside here. This first fact, it's easy and boring. I'll let you if you want to verify it. And actually the formula is not really that important, honestly. If you think about something that sends delta n to this topological n simplex that I was mentioning and glues things properly, that's the intuition you should have. But maybe I should say a few words about the proof of this adjunction statement. So we have, well, this is a lot easier with ends and coends. Of course, this is a one-line proof if you know what an end and a coend are. But let me be precise. So what is a map X to sing Y? Well, it is a natural transformation, so it is something that sends X brackets n. So for every here, this is sent to some sigma X from delta n into from topological and simplex to Y. And in such a way that for every F from n to m, so we have the pullback of sigma X is the composition. So for every X in, let me put an M here. For consistency, we have this guy, sigma X, and I pre-compose it with F here, and here is sigma of F of X. And that commutes. That's the condition of being a natural transformation, F upper star. So concretely, what is something that gives me a map from X brackets M to, so concretely, this is the same thing as exactly a map from this guy that respects the equivalence relation I wrote. And that's this condition here. That's respecting the equivalence relation. If you write it down, what it means. So that's the same thing exactly as a map from the geometric realization of X into Y. And that's the proof. And again, sorry, I'm being a bit fast in these preliminary sections because I don't want to spend a lot of time doing the technicalities, but please interrupt me if there are problems. Is it clear? Okay. Good. Good. For the sake of giving concrete examples, let me check one thing. So let's examine the geometric realization of delta 1 times delta 1. So what are the simplices? Of delta 1 times delta 1? Well, they are pairs of maps. F from n to 1, G from n to 1. So concretely, you can think of them as strings of zeros and ones. So you can think of this as 0, 0, 0, and then at some point it goes 1, and another 1, 0, 0, I don't know, 1, 1. If you write like the values of F in order. And the degeneracy is just doubling one simple. So we want to, so I guess the claim I want to make is that delta 1 cross delta 1 is the union of two simplices along a certain one simplex. So let me draw what I mean. So what are the vertices of delta 1 times delta 1? There are pairs. So there are 4 of them. And what are the one simplices? There are, as it turns out, there are 5 of them, of the non-degenerate ones. Then there are also the constant ones that I'm not drawing for simplicity's sake. But there are also 2 simplices. And this is the 2 simplex. So for example, sorry, just to, this is 0, 0, comma 0, 1. This one simplex here. This simplex here is 0, 1, comma 0, 1. This is 0, 1, comma 1, 1, etc. And the 2 simplices, the two simplices are 0, 0, 1, 0, 1, 1, and 0, 1, 1, comma 0, 0, 1. And you can see that they're not degenerate because the degeneracy is just doubling the same object twice, and you cannot obtain these from any lower dimensional guy. Well, for example, 0, 0, 1, comma 0, 0, 1 is just the zeroth degeneracy of 0, 1, comma 0, 1. So I'm not going to draw it because it's the degeneracy. But there are two non-degenerate simplex, which is surprising at first because in delta 1, all two simplices are degenerate, as you can easily verify. But when you take the product, two non-degenerate simplices pop out magically, even if both of their components are degenerate. And if you want, this corresponds to the fact that the projections sends these to degenerate guys, the two projections. And then I think I'll let you to verify the claim and see that, in fact, every higher simplex factors through one of these two simplices. Every higher simplex factors through one of those two simplices. And their intersection is exactly this 0, 1, comma 0, 1. So you actually have this push out. And so brackets delta 1 times brackets delta 1 is exactly a two-dimensional square.
I'm sorry to interrupt, but I think you have to be careful with that last claim because there could be simplices which are just generated at like one point.
They're still contained in one of these two simplices.
Oh,
maybe
right.
not in, I'm not saying exactly one.
Oh, right. Okay. Sorry.
I'm saying one. In fact, I'm saying I'm not saying it's a disjoint union, I'm saying it's a push out. Okay?
All right. Thanks. Sorry.
Okay. And in fact, we can rewrite this as brackets delta n times delta 1 times delta 1 mapping to the geometric realization of delta 1. Geometric realization of delta 1 is a homeomorphism. Okay, we have still 40. We're halfway through. Okay. Good. Okay, and this is a special case of the following proposition, which does need that we're working in compactly generated spaces for it to be true, but I am, and I'll never mention it again. So X, Y simplicial sets, the map, geometrical product to the product of geometric realization is a homeomorphism. This is perhaps not very essential, but it is useful to have around. And okay, and then I'm going to sketch the proof. Sketch of the proof is a reduction to X delta M, Y delta N, and then doing a combinatoric argument that similar to the one I did earlier, but I don't want to spell out in detail because it's a bit annoying. But I'll explain how you reduce to this case. Okay, so let's assume first Y is delta N. And let's prove it that for every X, this statement is true. So let us consider the poset of simplicial subsets of X A such that this map is a homomorphism. This is non-empty because you can just take any non-degenerate simplex, and this lives in here. And by Zorn's lemma, this has a maximal element. A. And here you need to use the fact that both sides commute with colimits. Because if you have a chain, you can write it as an increasing union of simplicial subsets, and then you can move the colimit outside. And here is where I'm using the fact that we're working in compactly generated spaces. We are using our top spaces RCG to show lengths where delta n commutes with colimits. But that's a minor point, but okay, just for the sake of being precise. So let A such a maximal element. Then let, if A is X, we won. Hey, that was easy. But if A is not X, we can find a simplex sigma from delta M into X, not in A, of minimal, actually let me call it, of minimal dimension. And this has to be non-degenerate, because if it were degenerate, it would be the degeneracy of something of smaller dimension. Sigma has to be non-degenerate. Otherwise, it would be in A. It would not be minimal. So we can take A prime, which is A union over the boundary of delta M along sigma. So it's the simplicial subset containing A and sigma. But then using the fact that, I cannot believe I already ran out of space, using the fact that these and these commute with colimits, commute with pushouts, we get a contradiction. Because this is saying that A prime is also in this poset, but this contradicts the maximality of A. Okay, and then need to find a better way to deal with this. Okay, then to prove it for a general.
Excuse me, could you quickly go back? I missed the last line. Thanks.
Yeah. This is a very standard kind of argument in simplicial sets. You want to prove something for a big guy, you know how to prove it for simplices, you take the maximal subcomplex for which the thing is true, and you show that you can add one single simplex. And well, and you're done. And just to quickly say in word, in words, the case of a general, to prove it for a general Y, you fix X and consider the poset of B in Y such that X times B goes to is a homeomorphism, and proceed as before. And again, I'm not going to do the case of two simplices that just direct combinatoric arguments, as in the case of delta 1 times delta 1. If you're curious, the details are in Gabriel Zisman theorem 3.1. It's a book about, the title is, let's see, Calculus of Fractions and Homotopy Theory. Okay. You have to, you consider a combinatorics of a set of paths from 0, 0 to nm, etc., etc. And I mean, actually, this is kind of the sort of argument that you use to prove how, I don't know, singular cohomology interacts with products. You need the cell decompositions of delta n times delta m. And that's exactly the same kind of argument. But you probably haven't seen it because everyone always skips it because the combinatorics is slightly annoying to write down. And hence I'm giving you a reference. Okay. That's a good moment to pause because I'm going to introduce scan complexes next. And I want to be sure that everything is all right so far.
Could you maybe explain again how we used that we are in compactly generated topological spaces?
Sure. So the fact we're using here is that if Z is a compactly generated topological space, you have this functor product, and remember, this product is not the standard product with the product topology, it's the product in compactly generated topological spaces. This has a left adjoint, which is mapped Z blank, again with compactly generated topology generated by the compact open topology. And so it commutes with colimits. In particular, I'm using that if you have a push out like this is the push out of this.
But didn't we use it only for Z equals the standard n simplex? And is this not on? Yeah.
Well, so first of all, you use it for a general X, for the, okay. Yes, you're right. But the point is that even if you take two compactly generated topological spaces and you take the product with the product topology, that is not necessarily compactly generated. So the general statement would be that, so this guy who is compactly generated is maps to this guy, which is not compactly generated in general, and this takes a compact generation, and this is a homeomorphism. If you weren't working in compactly generated spaces, we always have to be careful about this kind of behavior, which I don't want to be.
The fact I'm still a little bit confused is because this adjunction above you use this adjunction, and for Z equal the standard n simplex, this adjunctions should still exist on top.
Yes, but I'm also using it for the geometricalization of X here.
Okay. Thanks.
Okay. But again, I don't want to insist too much on that. I'm trying to be honest with you and motivate every statement I say, but I don't want to spend too much time on the technicality of simplicial sets because they're kind of beside the point. I just want you to have some kind of, to be somehow comfortable with manipulating them. Okay. Further questions?
Excuse me, could you maybe explain a little bit why this is the compact generation of the product and not the compactly generated product in the last statement?
Oh, that's the same thing as the compactly generated product. Sorry.
Oh, okay, thanks.
I mean, that's how the product in compactly generated space is constructed, because this
Thanks.
bracket CG is the left adjoint of the inclusion. It's the right adjoint of the inclusion of spaces in compactly generated, so compactly generated spaces into spaces. That's the co-localization. But okay, this way we can quickly get in category theoretic esoterica and. It pays off to be a bit comfortable with them, but on some level they're beside the point. Okay, now okay, are we ready to go further? Okay, so the next goal is to define homotopy groups. But for doing this, we need to ask something more of X. X, a generic simplicial set, is not going to be enough to define its homotopy groups. Okay, and kind of lying, you can sort of rig a definition, but that's well, okay. It will be clear in a second why it's better to ask something more of X. So for example, let's define pi 0 of X. Ideally, you want to take X0, the set of points, and quotient out by the relation X is equivalent to Y if there's a path from X to Y. But i.e. there exists gamma in X. Oh, sorry. Sometimes I write X lower n to denote the value of X at brackets n. That's standard notation. I'm trying not to use it right now, but okay, there is gamma such that the one face is X and the 0th face is Y. Remember, the ith face is the face obtained by removing the ith vertex. So the source is the 1th face and the target is the 0th face. Okay, that's the definition we want, but we have a problem. This guy is not an equivalence relation in general. And you can see, for example, for X equals delta 1, 0 is equivalent to 1 because there is the canonical one simplex that goes from 0 to 1, but 1 doesn't go to 0. There is nothing going in the opposite direction. There's some kind of directness. And that's unpleasant. That we don't want this. We would like paths to be able to go forward and backward. And for example, you can see what the problem is if you try to prove transitivity. So suppose you have gamma, a path going from X to Y, and delta, a path going from Y to Z. You can build it up into a map from delta 1 union delta 0 delta 1, which is this lambda 2 1 to X that I described before. And we would really, really like to build something from X to Z. So what we would really like is to fill these to a 2-simplex that will tell us what the path is. But this is not possible in general. For example, you could take X lambda to 1, and it's clear that you cannot do that. Okay. So in order to do that, we put a definition. So X simplicial set is a Kan complex if for every n, for every I, and for every map from this horn into X, remember lambda and I is the union of all the faces except for the ith one. There exists an extension f tilde from delta n into X. Okay, and it's clear how these, for example, in the case n2 and I1, this fixes the problem. So let me give an example. Oh, already out of space. I'm copying the definition. So let me give an example. Let Y be a topological space. Then sing Y is a Kan complex. So that's good. In a sense, Kan complexes, we should think of them as simplicial sets that behave like sing of something. So it's good that sing of something is indeed a Kan complex. So let's prove. Well, a map lambda and I into sing Y is the same thing as a map from the geometric realization into Y. And our goal is to extend it to delta n into Y, continuous map. But the inclusion lambda and I inside delta n has a retraction. For example, sending the ith vertex sorry, no, not the ith vertex, the barycenter of the ith face to the ith vertex and extending linearly. And let me draw it so it's clear what I mean. So this is the horn, that this blue piece here is the rest of the simplex. And what this map is doing is just projecting upstairs in a straight fashion. You can write it in formulas if you want, but I'm not sure if it's going to be clearer than drawing this thing. So you have a map, delta n to lambda n on topological spaces that retracts. So we have F. And we just define this extension of F tilde as the F composed with the retraction. And if you think about it, this is literally how we define the composition of paths in algebraic topology 2 or 1, depending on which year you took it. You pre-compose by this map, and then you restrict it to the simplex 0, 2. Okay. Good. I don't think I'm going to be able to define homotopy groups today, but I want to at least give you examples, or maybe I will be able to define homotopy groups. We'll see. Remark: if X is a Kan complex, the relation tilde on X0 we defined above is an equivalence relation. And I think I just gave you the proof of transitivity, in fact. And for the proof of symmetry, for example, if you have a path from X to Y, and you want to construct a path from Y to X, this is a map from to 0 to X, and then you can just extend it to delta 2. And you get a path from Y to X. And sorry, with this equal, I mean that the constant path, this SY, that I defined at the very beginning of today. S up a star of Y, I guess, to be precise. Okay, is it clear? Okay, let me give more examples of let me see, X. This is a symmetry. And transitivity is as before. You take a path from X to Y, a path from Y to Z, you extend to delta 2, and you get a path from X to Z. Let me give more examples of Kan complexes, though. So take X, Y topological spaces. And here enough, in fact, we can take it as ugly as you like. Don't need to be compactly generated here, technically, for this story to work. You can define map X, Y as the simplicial set and goes to continuous maps from X times delta N into Y. And notice that here points are exactly continuous maps, and paths are homotopies. So there's the intuition that homotopies are paths in some space. Here we can make it precise. Now, it's true that if X and Y are compactly generated, this is literally Sing of the mapping space. But the fun part of this is that this makes sense even when X and Y are not compactly generated, and you still get a meaningful object. And for example, pi 0, oh, sorry, I didn't say it. Map X, Y is a Kan complex. That exercise. And this might or may not end up in the exercise sheet, actually. I haven't decided yet, but it's an easy exercise. And so, for example, you see that pi note of map X, Y is exactly the set of homotopy classes of maps. So the notion that homotopy classes of maps are pi 0 of the mapping space is perfectly rigorous and perfectly precise, even for super ugly spaces. You just need to define the mapping space as a Kan complex and not as a topological space. And on this topic, I want to give you a slightly similar example that shows actually the power of this thing. Because this was kind of a stupid example, because for compactly generated spaces, it's just a thing of something. So you don't really need Kan complexes to make this, but okay. Let's Mn smooth manifolds now. And you can define Mn inside map Mn, the simplicial subset whose n simplices are maps n times delta n into n, such that for every t in this topological n simplex is an embedding. Is a smooth embedding. So points of Mn are embeddings, and paths are isotopies. This example is more meaningful if you've seen some differential topology, but hopefully most people here know what an isotopy is. If not, it's literally the definition I just wrote. And it's less obvious. So in the smooth category, this is still thing of something, but it's very hard to define. In fact, I don't think I've ever read the complete proof of this fact, that there is a topology on the set of embeddings for which paths are isotopies. It's called, I think, the Whitehead topology. But it's, honestly, I don't remember the details. It's very complicated. But what it boils down to, this is very easy to define, this Kan complex instead. Oh, I didn't say it. This is still a Kan complex. But okay, let me say it later. But in the PL category, if you work with PL manifolds, it's not known if this is thing of something. And that's very interesting, because when you do smoothing theory, you want to talk about the homotopy type of the space of embeddings. But you don't have a space of embeddings as a topological space. And that sounds like a deal breaker, but it's not, because you have a Kan complex of embeddings. And they just define it, and you can define it in like 2 lines. And everything is perfectly well defined, and it behaves as you want. So this is very powerful. These are very powerful tools. And okay, yeah, and let me say M as an exercise again. Again, it's quite easy. And Mn is a Kan complex. So in particular, when I will define the homotopy groups, we will be able to talk about the homotopy groups of the space of embeddings, and you won't have to be bothered defining crazy topologies, if they even exist, to talk about these homotopy groups. So this is an actual issue that you can solve with simplicial sets. An issue that in smoothing theory, so in a part of differential topology that actually asks you the question, oh, if I have a topological manifold, can I make it smooth? The answer is no in general, by the way. But you attack it by studying these spaces, the homotopy type of these spaces. So, okay. Are there questions?
Yeah, I have a small question. Is there an easy example of a Kahn complex where you can directly see that it's not the thing of some topological space?
In some sense, no. In fact, I'm going to show you next lecture that every Kahn complex is homotopy equivalent to the thing of some topological space. But you might want to ask, is it literally the thing of a topological space? So I think, yeah, there are such objects. You just need to find. Okay, but I don't know of any easy example, but they do exist. Kahn complexes are both literally more general, but also not really, because up to homotopy, which is all we are going to care about, there's not really going to be difference. In fact, that's going to be the main theorem of next lecture. I don't know if that was a satisfactory answer. But on some level, what I would like to say is that not a question you should ask. You really should be happy with Kahn complexes and somehow don't worry too much if they come from topological spaces or not on some level. But yeah, I realize this may not be a very satisfactory.
Yeah, I was just asking because I was a little confused because you said that you can write down this Kahn complex of embeddings, but there's no known construction of a topological space. And
well, I mean, the point is that if you have a Kahn complex, you know what the underlying set of the topological space has to be. It's just a set of zero simplices. And the question becomes, is there a topology on this set that makes this the thing of that set, of the topological space? And that's not known. I mean, it is precisely the precise there is no good notion of a topology on the space of PL embeddings, on the set of PL embeddings, sorry, of the space. But I'm not an expert of these details, so I can try to hunt it down the precise status of this question in the literature if you want. But I just wanted to put it as a slogan of, you know, a construction that's very easy to make with simplicial sets, and that's very hard, even unknown, how to do it with topological spaces. That was, I guess, the point. Okay. I have 10 minutes. I think I can give you the definition of homotopy groups. And then I think we can call it a day for today. Okay. I already defined pi zero. Okay, I didn't say it. Okay, pi zero is x0 modulo that equivalence relation. So let me write it down. 0 modulo this, just for the sake of having it written down. And the idea is we want a similar equivalence relation on higher simplices. So I'll write the general definition and I'll explain what happens for one simplices, and hopefully that will be clear what it means. So we have x0, keep using, sorry, S tau and simplices are homotopic relative to the boundary if there exists psi an m+1 simplex with forgot if the restriction to the boundary are the same, of course, otherwise that wouldn't make a lot of sense. And there exists an m+1 simplex with, let me get it right, its nth phase of psi is sigma, and its m+1 phase is tau, and for every 0 I n minus 1, the other faces, you have delta I of psi is the degenerate simplex corresponding to this. So concretely, what it means for n equals 1. So we have two paths, sigma and tau, and let's call x and y their boundary. And let's suppose that they have the same boundary. Psi needs to be something whose second phase is sigma. So we have sigma here, and whose first phase is tau, and whose zeroth phase is this constant guy at y. So if you think of these as paths, I'm asking to have a map from delta 2 into my space that's constant on the target. The target doesn't move, but it moves from sigma to tau. It's slightly different from the classical notion of a homotopy relative to the boundary, which would be a map from delta 1 times delta 1, but it should be clear that it is equivalent. So, example, exercise, actually. This is going to go in the exercise sheet, actually. I've already decided if x is string y, sigma tau from delta n into y are homotopic relative to the boundary, if and only if they are homotopic relative to the boundary of delta n to this simplicial, to this topological subspace in the classical sense. So this notion is a generalization of the notion that we have. And okay, let me just state a proposition and make a definition, and I'll prove the proposition next time. So proposition being equivalent, homotopic relative to the boundary is an equivalence relation on x n. Okay, and then we can define, so x can complex. Oh, sorry, if x is a can complex. That's why we define can complex, so that this theorem is true. And x can complex, x point of 0, then we take pi n of x comma x is the set of sigma and simplices such that sigma restricted to delta n is x modulo this equivalence relation. That's the nth homotopy group. Although I haven't proven it's a group yet, but okay. I think I'll stop here. Are there questions?
Yeah, I have a simple question. So, is there a non-example of a can complex?
Oh yeah. Sorry, I thought I gave it before, but delta n is not a can complex.
Oh, okay.
For example, because you can go from 0 to 1, but not backwards from 1 to 0.
Okay. Yeah, this
in general, actually, let me put this this other example, because it's going to be important in, I think, a couple of lectures. C category, and C is a Kan complex if and only if C is a groupoid. Kan complex are occasionally also called infinity groupoids for this reason, but this terminology will become clearer, I think, in a couple of lectures when I'll start talking about coherent nerve and coherent diagrams and etc.
Okay, thanks.
Oh, and probably I should mention that for this part, I'm following mainly Kahn's original paper that treats of these things, but there are plenty of references. In the notes, there will be many right pointers to the literature, but you could also just read the notes if you don't want to redo my job. The notes will probably appear, I think, tomorrow perhaps, or Saturday, I'm not sure, depending on when I finish writing them. Other further questions? Okay. Again, sorry for the lack of stable homotopy theory in these lectures so far, but it will come. Just give me a couple of weeks and we will start doing actual stable homotopy theory. And so let's call it a day for now, and let's see you on Monday. Thank you.
Bye.
Thanks.
Bye.
Bye.